Hey there, science fans! Welcome to another exciting journey into the world of physics and electricity. Today, we're diving into the electrifying world of Ohm's law, a fundamental principle that governs how electricity behaves in circuits. Don't worry, it's not as scary as it sounds. In fact, once you get the hang of it, you'll see how simple and intuitive it can be. Ohm's law is one of the most fundamental laws in electrical circuits. It explains how electricity flows through different components, making it essential for anyone interested in electronics. Just like how water flows down a hill, electricity has its own set of rules. Imagine water flowing through pipes. The same concept applies to electricity flowing through wires. Ohm's law helps us understand the relationship between three key players in this flow: voltage, current, and resistance. These three elements are like the main characters in the story of electricity. Think of it like a game of tug-of-war. Each element has a role to play, and together, they determine how electricity moves. Voltage is the force pulling the rope, current is the movement of the rope, and resistance is how hard it is to move the rope. This analogy helps us visualize the invisible forces at work. Understanding this relationship is crucial for designing and analyzing electrical circuits. Engineers and scientists use Ohm's law to predict how circuits will behave under different conditions. From the tiny circuits in your phone to the massive power grids that power entire cities, Ohm's law is everywhere. It's the backbone of modern electrical engineering. So buckle up and get ready to unlock the secrets of electrical circuits with the power of Ohm's law. By the end of this journey, you'll have a solid understanding of how voltage, current, and resistance interact to make our world run smoothly. Whether you're a budding engineer, a curious student, or just someone who loves to learn, Ohm's law is a fascinating topic that opens up a world of possibilities. So, let's get started and explore the magic of electricity together. Remember, every time you flip a switch or charge your phone, Ohm's law is at work, making it all possible. Let's dive deeper and see how this incredible law shapes our everyday lives. First up, let's shed some light on voltage. Imagine a battery with its positive and negative terminals. Voltage is the oomph, or electrical potential difference between these 2 points. It's the driving force that pushes electrons, those tiny charged particles, through a circuit. Think of voltage like the pressure in a water pipe. The higher the voltage, the greater the pressure, and the more oomph those electrons have to flow. We measure voltage in volts. A standard AA battery, for instance, has a voltage of 1.5 volts. Now let's talk about current. Current is the flow of electric charge through a conductor, like a wire. It's measured in amperes or amps, and it represents the rate at which those tiny electrons are moving. Imagine a river flowing. The wider and faster the river, the greater the current. Similarly, the higher the current in a circuit, the more electrons are flowing past a point each second. Difficult it is for current to flow. Section 5. Ohm's law in action, the formula. Now that we've met our key players, let's see how they interact. Ohm's law is a fundamental principle in electrical engineering that helps us understand the relationship between voltage, current, and resistance in an electrical circuit. This law is named after the German physicist Georg Simon Ohm, who first formulated it in 1827. By understanding this law, we can predict how electrical circuits will behave under different conditions, which is crucial for designing and troubleshooting electrical systems. Ohm's law states that the current, denoted as I, flowing through a conductor is directly proportional to the voltage, denoted as V, applied across its ends, and inversely proportional to the resistance, denoted as R, of the conductor. This means that if we increase the voltage, the current will increase, provided the resistance remains constant. Conversely, if we increase the resistance, the current will decrease, assuming the voltage remains unchanged. This relationship is neatly captured in the following formula: Vi equals Y times R. This formula is not just a theoretical concept, it has practical applications in everyday life. For instance, it helps us understand how electrical devices like light bulbs, heaters, and motors work. By knowing the voltage and resistance, we can determine the current flowing through these devices, which is essential for ensuring they operate safely and efficiently. Where V stands for voltage in volts, I stands for current in amperes, and R stands for resistance in ohms. These units are standard in the field of electrical engineering and are used universally to describe electrical properties. Voltage is the potential difference that drives the current through the circuit, current is the flow of electric charge, and resistance is the opposition to the flow of current. This simple formula is incredibly powerful. It forms the basis for much of our understanding of electrical circuits and is used extensively in both theoretical and practical applications. Engineers and technicians use Ohm's law to design circuits, troubleshoot problems, and ensure that electrical systems operate within safe parameters. It allows us to calculate any of the three variables if we know the other two. This flexibility makes Ohm's law an indispensable tool in the field of electrical engineering. Whether you're working on a complex industrial system or a simple household appliance, understanding Ohm's law can help you make informed decisions and solve problems effectively. For example, if we know the voltage across a light bulb is 12 volts and its resistance is 6 ohms, we can calculate the current flowing through it. This is a practical application of Ohm's law that helps us understand how electrical devices function. By knowing the current, we can ensure that the light bulb operates within its safe limits and avoid potential hazards like overheating or electrical fires. I equals V divided by R, which is 12 volts divided by 6 ohms, equaling 2 amperes. This calculation shows that the current flowing through the light bulb is 2 amperes. Understanding this relationship helps us design circuits that are safe and efficient, ensuring that electrical devices operate as intended without causing damage or posing risks to users. Section 6. Real-world applications of Ohm's law. Ohm's law is not just a theoretical concept, it's the backbone of countless electrical and electronic devices we use every day. This fundamental principle, which states that the current through a conductor between 2 points is directly proportional to the voltage across the 2 points, is crucial in understanding how our modern world operates. Here are a few examples that illustrate the practical applications of Ohm's law in our daily lives. Light bulbs. The brightness of a light bulb depends on the current flowing through it, which is determined by the bulb's resistance and the voltage applied. When you adjust a dimmer switch, you're essentially changing the voltage, which in turn affects the current and the brightness of the bulb. Electric heaters. The heat generated by an electric heater is directly related to the current flowing through its heating element, again determined by Ohm's law. The resistance of the heating element and the applied voltage dictate how much heat is produced, making it possible to warm up your space efficiently. Mobile phones. From the battery to the intricate circuits, Ohm's law governs the flow of current, ensuring the proper functioning of your phone. The law helps in designing circuits that manage power consumption, battery life, and overall performance, making your device reliable and efficient. Power grids. Electrical engineers use Ohm's law to design and manage power grids, ensuring efficient and safe distribution of electricity to our homes and businesses. By calculating the optimal resistance and voltage levels, they can prevent overloads and ensure a stable supply of power, which is essential for the functioning of modern society. Automotive industry. Ohm's law is also crucial in the automotive industry. The electrical systems in cars, from the headlights to the infotainment systems, rely on precise calculations of current, voltage, and resistance to function correctly. This ensures that all components work harmoniously without causing electrical failures. Computers and IT. In the realm of computers and information technology, Ohm's law is fundamental in designing and troubleshooting circuits. Whether it's a simple desktop computer or a complex server, understanding the relationship between voltage, current, and resistance helps in optimizing performance and preventing overheating or short circuits. Renewable energy. Ohm's law is also applied in renewable energy systems, such as solar panels and wind turbines. Engineers use the law to design systems that maximize energy conversion efficiency and ensure that the generated power is safely and effectively distributed to the grid or stored in batteries. In conclusion, Ohm's law is a cornerstone of electrical engineering and technology. Its applications are vast and varied, touching nearly every aspect of our modern lives. Understanding this fundamental principle not only helps in designing and maintaining electrical systems, but also in innovating new technologies that drive progress and improve our quality of life. Section 7. Conclusion. The power of Ohm's law. Ohm's law is a fundamental principle in the world of electricity. It provides a clear and concise way to understand the relationship between voltage, current, and resistance. This simple law has far-reaching implications, enabling us to design, analyze, and troubleshoot a vast array of electrical and electronic devices. From the smallest circuits to the largest power grids, Ohm's law is always at play. So, the next time you switch on a light, charge your phone, or simply marvel at the wonders of technology, remember the power of Ohm's law.